Crane Software. He is a technical at VLSI and embedded system. Over to you, YGP sir.
Thank you, ma'am. A warm greeting and welcome you all to the fifth session of ATAL FDP on Advanced Embedded Systems, RTOS and Automotive CAN Applications. Empowering the future of technology start with mastering the systems that drive it. Let this FDP on embedded systems, RTOS and automotive CAN applications be the spark that ignites innovation and excellence in our career. I am Praveen Kumar YG, Associate Professor, Department of ECE SSIT. Feel privileged to introduce the today's speaker, Mr. Mohsin Khan, who will be talking on synchronization and semaphore. Mohsin Khan, a highly accomplished domain expert and corporate trainer specialized in VLSI design, verification, and embedded automotive systems. With more than 14 years of expertise in training and IT, he has contributed immensely in building skilled engineers for semiconductor and embedded industries. His technical mastery covers a wide spectrum, including HDLs, System Verilog, UVM, Python, Embedded C, RTOS, and Simulink. Over the years, he has delivered more than 25,000 man-hours of impactful training, guiding the careers of over 2,000 students and 200 plus careers corporate engineers. Mr. Khan is recognized as a preferred trainer for VLSI and embedded systems, conducting numerous workshops enriched with hands-on sessions that effectively blend academic learning with industry requirements. His dedication to mentorship, innovation, and practical skill building has made him a trusted resource for both academia and corporate sectors. Sir, we are privileged to have you with us today, and we are looking forward to learn from your vast experience. With this brief introduction, let me hand over the session to Mr. Mohsin Khan. Sir.
Hi, good evening, all of you. Thank you, Praveen sir. Thank you for briefing about myself. And it's my privilege to be part of this
Hello.
program
Hello.
Hello, I'm audible there?
Mohsin sir.
Yes.
Hello.
Hello.
Mohsin sir.
Yes, I'm audible there?
Mohsin sir. Hello.
Yes, can you hear me, madam?
Yeah, we can hear you.
Yeah, I think there was some glitch.
Okay.
Yeah, thank you, Praveen sir, for introducing me and providing a brief, broad information about myself for the audience. And it's my privilege to be part of this session today as a resource person. Yes, today I'm going to speak on synchronization and semaphore concept, which is part of real-time operating system. And RTOS is, it is used everywhere, wherever we need real-time control, okay, real-time response. Mainly, I think this FDP is focused majorly on automotive segment. Anyway, so we are going to start our session. Let us share the screen over here. So okay, so I believe the screen is visible. Yeah, can somebody confirm the screen is visible over there?
Yeah, it's visible, sir.
Yeah, thank you. Okay, team, I can see we have professors, faculty members from various universities and engineering colleges, and they might be expert in their domains, and they might have handled lots of subjects in their experience. And it's uh, teaching role is always a kind of continuous learning, and we are never going to stop learning. And of course, knowledge sharing between us as well as the external resource people. And anyway, this is a right platform where we can share knowledge and pass on this to the rest of the others, so that the knowledge keeps growing. Okay, so here we start with RTOS synchronization and semaphores. I believe in the previous sessions, you guys might have already gone through certain concepts of real-time operating system. And Okay, so I'm not going to, you know, go in depth again with respect to RTOS because we have our own agenda. Like we are going to talk on the specific topic, like going to have a better understanding of a specific topic, which is part of this real-time operating system. Okay. So in this, the topic is synchronization and semaphores. So before I talk about these topics, uh, yeah, of course, we are going to have some introduction or some basic concepts recall. Okay. And then we'll be finally connecting with the main topic of today's session. Okay. And also, we are going to understand or discuss some practical use cases about this synchronization and semaphore processes, especially used for automotive applications. Okay. Yeah. So here we have the agenda. Like we are going to talk something on operating systems, process synchronization, and then we are going to have a kind of practical Linux examples where I will be demonstrating some example programs related to this synchronization and semaphore concepts. Okay, and also I just want to add one more point, like somewhere in between, if you uh, f- feel some kind of uh, hearing or like technical glitches, if you find some technical glitches, like you're not, like I'm not audible or the screen is not visible, please keep updating me. Okay. And also you guys might get some questions in between. Yeah, of course, we'll take up your questions. Okay. And you can keep posting in the chat, and we'll have a separate a few minutes for questions and answers. Okay. So then we'll be taking your questions. Okay. Yeah. So as I said, we'll be starting with just basic definitions, just a kind of quick recall. That's it. Like we are not going to elaborate that. Okay. So we'll be focusing more with respect to our today's topic. Okay. So these are the few topics, few points you can say, which we will discuss. Okay. And then we will elaborate more with respect to synchronization. Okay. And need of synchronization, and what is race condition, and what are the critical sections, and what is the need of semaphores. Okay. How these semaphores are useful. Okay. In this synchronization, especially when it comes to operating systems. Okay. So like we might be relating more towards RTOS. Like already we know we have GPOS and RTOS, right? Okay. So these things already you guys might have come across while handling subject, those who are already taken this subject, operating system. So as we have a mixed crowd, so many of you are here, might be some of you might have not taken the subject. Yeah, just for quick understanding, I have just added some points here. Okay. So if you look at here, basically when we talk about operating system, we have a general purpose operating system and we have real-time operating system. So what is the major difference? The major difference is like the time constraints. You know, we are okay if there is some time delays for processing or computation in general purpose operating system, but we are not okay with real-time operating system. So that's why the name given, real-time operating system, right? So real-time operating system is something which is going to manage the processes, the task within that system in such a way that all the tasks are completed, handled, and taken care within the given deadlines, within the time constraints. Okay. So that means real-time operating system guarantees the execution of the processes or tasks within the given time constraints, and they exhibit the deterministic behavior. That means we can determine like this task will get complete within this time, like deterministic behavior. And time critical applications, we where we use normally we use real-time operating system for time critical applications. Okay, so there are so many time critical applications. Let us consider automotive is one of the area where we have critical applications. Okay, like for example, airbag opening system, right? And not only that, we can also take aircraft, aerospace industry applications, where we have lots of critical applications where the operations or the processes has to be completed within deadline, or else it will result into system failure or fatal error or damage. Okay, a critical loss can happen if the things are not managed within time. Okay, and operating system real-time operating system, they exhibit preemptive multitasking behavior. Okay, like in one system you have scheduled multiple tasks. So you have multiple tasks that has to be taken or executed by one system, and those tasks are managed by the kernel, and kernel will have the scheduler, and scheduler will be scheduling those tasks, and there are certain policies which will be followed. Okay, so that a timely execution of the task happens while switching the task, context switching, as well as managing the priorities. Okay, so all these things will be taken care by the operating system, actually the core of the OS, that is the kernel. Okay, anyway, I will just show you some diagrams where you can have some better understanding. Okay, so coming to key characteristics, yeah, of course, we are going to talk about hard real-time systems. Missing deadlines will result into great loss, damage, nothing but system failure. And soft real-time, so occasional deadline miss is acceptable, but not always. So another characteristics like priority-based scheduling. This is one of the most important characteristics of any operating system, but it is more important with respect to real-time operating system, right? And low latency interrupt handling. So again, only executing task is not the responsibility of the real-time operating system. It should also take care of the interrupts, okay, providing service for the external uh, resources, external peripherals. So it has to quickly respond for the request, nothing but low latency interrupt handling. So within short time, it has to provide the response and service to the service requesting device, right? Okay, so coming to the operating systems, in market, you will find hundreds of real-time operating systems. So if you look at here, in the last line, I have listed some real-time operating systems like FreeRTOS, VxWorks, QNX, RT Linux. So these are all the real-time operating system that are built and introduced by different companies, and they are used in different products. Okay. So for example, VxWorks. VxWorks is the operating system, real-time operating system, which is a product of Wind River company, and it is used mainly in router applications. See, you might have seen routers in your surrounding. Okay, so even that router is an embedded product, and that embedded product uses real-time operating system for handling the task or multi-processing in real time. So, router is very important, like it has to manage the network traffic. And VxWorks is one of the real-time operating system which is specially designed for router applications. Okay, if you look at one more, I have listed there, QNX. So QNX is another real-time operating system which is majorly used in automotive industry. Okay, like you might have lots of questions like why they have come up with so many different real-time operating systems, right? See, even you guys can design and come up with your own operating system. Okay, uh, guys, I believe somebody has to mute the. Okay, thank you. Okay, see, what I was telling here is there are hundreds of real-time operating systems where even you can come up with your own real-time operating system, but you have to make sure that your operating system is doing better with respect to multitask handling and meeting the deadlines. And you can focus for a particular application and you can introduce your operating system. Okay, if you look at here, FreeRTOS. So FreeRTOS is another real-time operating system, which is a product of Amazon. Okay, so Amazon introduced this and they have both versions, free version and premium version. And FreeRTOS is given freely so that students can, you know, port this in respective hardware microcontroller, and then they can utilize this real-time operating system as part of the project. Okay, so whatever the embedded application projects they are working on, right? So just like that, we have so many operating systems. One more I have listed, RT Linux. So there are hundreds of operating systems. You can just search in internet. Uh, Everybody introducing their own operating systems. Okay, but the main uh, idea behind this is the real-time operating system should be designed in such a way it should guarantee the execution of the task within given time limits. Okay, right. So let's move on. Okay, so if you look at this diagram, see, more we understand or better we understand whenever we look at a picture, right? So if you look at this diagram, you can see we are showing some system, and we are also showing few tasks here, okay? And few files are available here, and some peripherals are there, okay? So that means the system, all these tasks will be running in the system to provide service to these peripherals or to do some other operations. And along with that, the task might also be using the data from the files, like they might be reading data from the peripherals and storing in the file, or they might be getting data from the file and giving to the peripherals. So all this behavior will be defined within the task. So multiple tasks might be running in your system. Okay, your system might be running multiple tasks, but who is managing these multiple tasks in your system? So obviously you would answer like operating system, right? So there is an operating system which is handling all this multitasking, and it is responsible for all these things. Okay, what are the main functions of operating system? You can say like, of course, operating system has kernel inside, and the kernel is the OS, and that core of the OS, and that kernel is responsible for file management, resource management, memory management, scheduling, task management, inter-process communication, interrupt handling. There are so many, important functions that are performed by the kernel of the OS. And that's how we generally call operating system is handling everything. But actually, the kernel inside the OS is doing those jobs. Okay. So now the intention of showing this diagram is GPOS. Okay, so initially I added one point. Like basically, we divide operating systems into two categories. One is general purpose operating system, another one is real-time operating system. Okay, see, normally the operating system which is running in your laptop or computer, or even you take your smartphone, okay, Android phone or Apple phone. Okay, so they're all also having operating system, and they are all categorized as GPOS, general purpose operating system. Okay. Then what about RTOS? See, RTOS is actually designed for single core hardware. Okay. So you need to remember that. Anyway, I'm going to bring out a list of the differences between GPOS and RTOS so that you can have even better understanding when you can see like where and when I will use GPOS for what systems, and when I will use RTOS for what systems. Okay. Right. So just quickly look at one more diagram. You will just find out, you can link something, right? So here you have seen a system with uh, multiple tasks, and there is a task scheduler, that is a scheduler which is going to be part of the kernel. And kernel is responsible for the task scheduling, okay, as well as for resource management, as well as for memory management, file management, interrupt handling, or interprocess communication. So many important functions as part of the operating system, right? Okay, so just look at one more diagram here. Okay, see, I'm showing one more diagram. Now I think you can relate. See, the previous one, a laptop is shown here, and here a microcontroller is shown, that is ESP32. So if you look at this, so what do you feel? That means even we can have a small operating system running within this small microcontroller chip, right? So that's what we are talking, like real-time operating system. Okay. See, usually real-time operating system, it is designed to work on single core processing systems. Okay. See, if you look at inside this microcontroller, okay, so by looking at this diagram, you can easily say this is ESP32, and it is having an SoC chip from S plus F systems, and the processor inside this is uh, made using the architecture. It is built using the architecture extensilica. So you might have heard, like, we have different processor architectures, ARM processor architecture, ARM architecture, and x86 architecture. So like that, we have so many architectures, MIPS architecture, RISC-V architecture, etc. Even somebody has come up with their own processor architecture. Let us assume, yeah, this is a China product. Like the company has come up with their own processor architecture. The architecture of the processor is extensilica, and it's a 32-bit processor which is part of this SoC chip, and that SoC chip is nothing but your ESP32, right? Okay, so this is a more advanced microcontroller, you can call, because it has so many advanced peripherals embedded, integrated within that. And but one thing you need to understand, like, this is not in anywhere in competition with your laptop, right? Because that is processor based system purely having all the resources external, off chip, like on motherboard, whereas here on chip, right, everything is on chip. Here the memory is limited, fine. So if you look at the features of any microcontrollers, normally you will come across the limitations as memory and the number of IO pins, and the peripherals which are inside that, and even the processor which is going to be part of this microcontroller chip. Inside microcontroller, it is majorly of single core, right? Single core, dual core, octa core, uh, quad core, octa core, hexa core. Okay, we can have multiple cores, processors with multiple cores nowadays. And RTOS is specially designed for a chip, a microcontroller chip, which is having a processor with single core. So that's the main intention. And also the what we call it as the size. Okay, the size of this RTOS is very, very small. So you might ask, like, what will be the size? So something around 80 MB. Just think you have a small operating system within a size of 80 MB. So if I just ask you what is the size of operating system in your uh, laptop, so like you're using Windows or Ubuntu or Mac OS, they are usually in terms of GBs. Okay, 15 GB, 20 GB, like that. Okay, so now, so what we need to understand here is there is a small OS, and we are calling that as RTOS. Why? That OS is specially designed for small chips, to run on small chips, and it has ensured that the OS or the kernel within that OS is responsible for this multitask management. And it is designed in such a way that kernel is able to handle that multitasking and complete them within the given deadlines, within the time constraints. This is, I'm repeating multiple times, RTOS, like real time. When we say real time, it's going to perform the operations within given time. Okay, that's why we are calling RTOS, or else we can call this as GPUs. Okay, so now the footprint is very small, the size is very small. Okay, and you can see this controller can also do the similar operations what your system, but not the huge ones like how your system does. So here we have limited memory, and it will be able to do multitasking within that limited memory along with operating system. Okay, that means I am telling that you're going to combine the real-time operating system with the applications, and that applications are converted into multiple tasks, and those tasks will be managed by the real-time operating system finally to handle the operations within that small system, okay, for particular application for whatever you have designed this, right? Okay, so you can also see this diagram. You can easily understand user application program RTOS. That means here RTOS is integrated, or you can say like application programs are integrated with RTOS together, and then they are going to run on the hardware. So hardware, nothing but the processor, which is part of this SoC chip, what you are seeing here on this microcontroller. Okay, right. So now you got a complete clarity, GPOS, RTOS. So now I would like to add one example. See, if your mobile hangs for few seconds, it doesn't create huge loss, or it doesn't create a great damage, right? See, if your mobile hangs, hardly what you will do, you will wait for a few seconds, or it might come back, or if it doesn't come back into normal mode, then you might restart that. So there is no loss, no damage. What if the airbag opening system in a vehicle does not open for a few seconds after an accident detection? See, there is an accident detection, but airbag is not getting opened within the time, within the deadline, within the time constraint. It is taking 5-6 seconds extra to open. Then just imagine the loss, the great damage. So a life will get damaged. That means that's a critical application. So in such areas where we have critical application, I don't say like you have to use RTOS everywhere. So for example, you're building a smart washing machine, you might not need real-time operating system. Or even if you bring no issues. Okay. So you're building a smart refrigerator, you might not need real-time operating system as part of the project, or you might bring. But for critical applications where a great damage can happen, definitely, of course, you need to bring RTOS as part of the project. Okay, right. So if you look at this diagrams, again, this will give you even some more a better understanding of GPOS, your typical operating system configuration, and typical embedded RTOS, real-time operating system. So here you can see the user programs are integrated along with your operating system. And here your operating system is separate. User programs are running on top of your operating system. Like you can install and uninstall the applications just how you do in your mobile phone. From Play Store, you will install the application, and whenever you don't want, you uninstall that, right? Because you have user interface with the OS which is running in your device, as well as you have the package manager which will help you for installation and uninstallation. So that is happening. But here it is not like that. So you're going to pack your application along with your operating system, and together you will generate the hex file, and that hex file you're going to flash in the microcontroller. Then what happens? You don't have that flexibility of detaching the user application with the RTOS if it is already combined and compiled into a single hex file, and that is running on the hardware on that particular chip microcontroller, right? Okay, so this will also give you a better understanding of differences, okay, between typical OS and embedded systems. Okay, so just quickly try to understand the differences. So again, this is very important. As I added few points earlier, you can see there, multi-core system, single core system. Okay, so multi-core. So what exactly multi-core? Why we are calling multi-core? See, a core is nothing but the ALU within your processor. Okay, see, if your processor has more than one ALU, then we can say it's a multi-core. If your processor has just single ALU, then we call it a single core, right? Okay, so that is the main difference. Now, if, as I said, RTOS is specially designed for the processors which are having single core, and whereas GPOS is designed for multi-core processors. Okay, and GPOS can do multitasking, whereas in RTOS, multitasking is not supported, context switching is supported. Now you might think like, why multitasking is not supported? Because we have only one core, one person, one worker, right? So in multi-core, we have four workers. Let's say four workers, they do four different tasks. Whereas in single core, single worker, he cannot do four different tasks. He has to switch the context. Like he should give some time for task one, some time for task two, some time for task three, and some time for task four. Okay, so that's how it works. So here in RTOS, it is context switching, whereas in GPOS, multitasking, and multitasking possible only if you have multi-core, not with single core, right? Then non-time critical applications. Yeah, of course, as I said, uh, your mobile phone, it doesn't have, critical, very critical application. Like even if you consider you are on a call and that call is also somewhat, if it disconnects and your processor is not able to handle that call for few seconds, again, it's not a great loss, but that's not the case in critical applications. That means here we mainly use RTOS for time critical applications. Okay, so that's clear. Then coming to GPOS, unpredictable. Here it's a predictable system. Yeah, of course, we have dedicated deadlines. We have designed the OS in such a way it will ensure that the things gets completed, the task gets executed within the given time limits. And footprint. I think this point already I added earlier. Like the RTOS comes in MBs. Okay, you can go and download the official RTOS from official websites. Like let us say free RTOS. So if you search in Google free RTOS download, you can go and download that. So they will give you the complete source code for free RTOS, which you can import to a particular microcontroller, and then you can uh, bring the behavior of RTOS as part of your application. Okay, so coming to footprint, this is in MBs, this is in GBs. Now coming to latency. So latency is high here. Response time is, it takes more response time here, the less response time. And one more thing here, supports only few hardware platforms, whereas here it supports wide range of hardware platforms. Okay, because multi-core systems and single core systems, that will differentiate, and works with GUI. So best example, your smartphone. So you have OS, Android OS running with GUI, whereas if RTOS is integrated along with your application and compiled and generated a hex file and it is flashed in the microcontroller, then where is your GUI? Like you're not bringing any GUI, especially in small microcontrollers, because they already have less memory. They cannot have more and more software layers so that you can bring more and more behavior. So we are not interested in GUI. We are interested in handling the task within the device in real time. Okay. And coming to the last point, it is normally used for desktop PCs and laptops or mobile phones, as I said. So it is only applied to the embedded applications, just like I have shown in this diagram. So RTOS is used here and your GPOS is used here, right? Okay, so now you have the clarity of both general purpose operating system and real-time operating system. Okay, let's come back to another important uh, topic, that is kernel. Okay. So now kernel, I think those who have already handled the subject operating system, they might be aware of what is kernel, and they might have gone through so many features of kernel. Of course, uh, um, this is something which is important, especially when it comes to systems. As an electronics engineer, we might always think like my job is like just IC design or hardware design. Okay, so I'm sorry, like you have to be more good enough in programming as compared with software engineers, especially when it comes to the core part. Software is going to talk with hardware. Okay, and how that software is going to talk with hardware, only when you know the actual hardware, then only you can write the software to connect the software with the hardware, that is device drivers. Okay, so now coming to here, kernel, it is in the OS. So your OS is built with kernel, you can say like this. See, somebody wants to build OS. Okay, how you are going to start? The first question. So the first question is, you have to take the kernel, on top of kernel add the additional layers of software, and then build your own OS. Okay, who will give you the kernel? Two options. Either you build the kernel from scratch, or you take the kernel, somebody has built that. You have two options. Let's say I am taking a kernel somebody has built. Then what is the guarantee that kernel is having the real-time behavior. So again, it's a challenge. That means there are companies, they are building their own kernel. On top of that, they will add additional layers and then they will pack as a OS, nothing but their OS with their behavior, with the behavior what they have actually brought. Okay, it might be GPOS or RTOS. Fine. So why I'm showing this diagram here, the reason is, first thing you need to remember, kernel is the core of the OS, and all important operations in
Excuse
operating
me.
system, they are performed by kernel. Yes, yeah. Anybody have questions, you can ask me
Yeah.
further. Yes.
Actually, tell something about the RTOS kernel versus normal kernel difference, and as well as how the RTOS multitasking will take place and interrupt handling in RTOS. I need these three.
Yeah, of course. So I think we have interrupt handling topic. We have one more session on Saturday, interrupt handling and CAN protocol. Today I will be covering. I can tell you, I can bring in between interrupt also. I will add that point. More detail there we will elaborate in Saturday's session. Today, as you requested, I will add some points with respect to that. So other than that, okay. So you were asking questions about the differences between this kernel.
Normal and
Yeah,
RTOS.
yeah, normal kernel and RTOS kernel. Correct. So, correct. So,
Thank
good
you.
question. Yes. See, if you look at here, so you can see some of the important functions that are performed with the kernel, they are shown here, right? Okay. So, what are the operations that are performed or that are done by, taken care by the kernel? So, one is task management. Another one is synchronization and communication. And next one is memory management, timer management, interrupt and event handling, and device IO management, and even more. Like these are the few important operations that will be taken care by the kernel. Okay. So now coming to the difference. Okay, see, as today's agenda, like I will be focusing a little bit more on synchronization and communication, like semaphore concepts, semaphore and mutex, which is mainly used for synchronization between the multiple tasks. Like task management will be handling tasks, okay, multiple tasks. But when the tasks are executing, they might be using shared resources, then they might end up with the conflicts or race conditions. To overcome those race conditions, they introduce the concept of synchronization. In that, they introduced semaphores and mutex, etc. Anyway, we are going to elaborate and discuss more details about that. Okay. So coming to here, I will just show you one diagram. Uh, okay. So just look at this diagram. See, here you can see like we have a microkernel. Okay. So on top of this kernel, we don't have any additional layers. Just think here, like we have a device driver layer. Okay, on top of hardware, we have device driver layer. On top of device driver, we have microkernel. Okay, a kernel, you can say like kernel. Again, we have different types of kernel, monolithic, microlithic, etc. Okay, and okay, so who is going to, you can say like device drivers are part of kernel, you think like this. So these device drivers, they are part of kernel, and this kernel is part of OS. But now when it comes to OS, there are so many additional layers, system software. Okay, like you are not finding maximum layers with respect to system software, whereas you are finding hardly the device driver, which is basically used for hardware communication, and then the microkernel. Okay, and then the task. Okay. So now coming to here, uh, the tasks are directly attached with the kernel APIs. Think like that. Think like, let us say you have task one, task two, task three. They are directly talking with the kernel. In between the task and the kernel, there are no additional layers. Okay. Whereas if you take GPOS, general purpose operating system, then you can say there might be so many additional software layers between the task and the kernel. See, actually the task talks with the kernel and kernel talks with the hardware. But to talk with the hardware, kernel needs device drivers. Okay, so that's why device drivers will be part of kernel. Okay, fine. So here, one thing you have to understand, between a normal operating system and real-time operating system, the number of layers above the kernel will be less or no layers on above kernel in RTOS, whereas there will be lots of additional layers if you go with normal operating system. Okay, so that is the main difference you can find. Okay, for example, uh, just for clarity, I will quickly show one picture, just one picture for you. So Android OS layers. So I'm just to show you that diagram, I'm opening this one. Okay, so just look at this diagram. Uh, okay, let's open this in new image. Okay, so if you observe this, see here we have kernel, Linux kernel, and on top of kernel, okay, the kernel can be from Linux kernel, or a kernel you might have built that. Okay, so on top of kernel, you can see there are so many layers before it reaches to the application. Application is on top. So you have hardware abstraction layer, libraries, static libraries, runtime libraries, application frameworks, then application. So if the application wants to talk with kernel, it has to pass through all these layers. Then it has to talk with kernel. And then kernel will talk with hardware using the drivers, which are already part of the kernel. Okay. Like you have Bluetooth driver, camera driver, USB driver. They are all part of kernel. Okay. So this is how you will find normally in your GPOS. But if when it comes to your real-time operating system, I think somebody is writing on the screen. Can you please stop that? Okay. Okay. So now coming to here. Okay, just give me 1 second. Okay. So, uh, guys. Okay. So I was talking about this. Let's come back to our agenda. Yeah. So I believe you got some idea. Okay. Let's get back. Okay. So now, yeah. So now coming to kernel, kernel is the main uh, responsible person. You can say it's the responsible part of the software in the OS. And RTOS, you can say your entire RTOS is majorly a kernel. And you will find very limited additional layers on top of kernel. That's why it's making more faster and quickly response for the task, as the direct communication happens from the between the task and the kernel and the kernel objects, so that uh, that can get executed in the hardware. Okay, like see, these are all kernel objects. So scheduler is the kernel object, memory manager, timer, and synchronization. Okay, so our agenda is here, right? So synchronization. So let us focus on synchronization. Yeah. So there are so many concepts which comes under kernel, and synchronization is something which is very important. Like let's say, for example, you have some shared resource. Task one is also using that shared memory, and task two is also using the same memory, shared memory. So what happens if both the task try to access the memory at the same time? Then what happens? Clash will happen. So we call that as a race condition. Then how to handle that race condition? So when task one is using that shared memory, task two should not use that. Okay, or task three should not use that. So we have to bring some kind of you know uh, mechanism, you can say some kind of mechanism or some kind of synchronization, which will ensure that when task one is using the resource, task two should not use that, or task three should not use that. So that the race condition will not happen, and that will not result into unexpected outcomes. Okay, so normally this will result into unexpected behavior, like task one wrote something, task one is putting data of sensor one, and task two is putting data of sensor two, and simultaneously both try to put there, and task one was able to put, but task two was not able to put, but you miss the data from sensor two. At that time the action was not performed based on that particular time event. Okay, so there are lots of conflicts happen when multiple tasks, they are accessing the same resources. Okay, so to handle that particular scenarios, like both the tasks trying to access the critical section, okay, critical section or common hardware resource, so these problems have to be overcome. For that purpose they introduce the concept of synchronization. Okay, so I will just come back here. Okay, so now see, normally we have uh, inter-process communication. Okay, so generally what happens, one process sends data to another process, and that is inter-process communication. And now we are not talking about IPC, we are talking about two processes, or you can say two tasks, or you can say two threads. Okay, two process, two tasks, two threads. Okay, when these two process, two tasks, two threads, they're trying to access the same shared resource, then the conflict happens, then the race condition occurs. So that might result into unexpected outcome. That means we might not get the correct output what we are exactly expecting. I will show you that with some example. We'll see that. Okay. Okay. Let us see here. What is the need of synchronization? See, the problem is race condition. See, whenever we get this race condition, so we need to solve this. The race condition is nothing but you have one chair, two people trying to sit on the same chair. Okay. And every time they are in race I will sit. Okay, so that has to be avoided. Okay, so for that they have introduced the concepts of something called semaphores and mutex concepts. Again, in semaphore they have introduced binary semaphore and binary semaphore binary semaphore and counting semaphore. Okay, and a mutex concept. Anyway, we are going to have detailed understanding of this concepts. The concepts are, they are simple actually, and we can easily understand in simple way. And also, I will show you some programming examples by running and connecting the relation and the concept of what exactly this semaphore concept and mutex concept. Okay, and even what we say this counting semaphores. Okay, so if you look at this, just I have shown you some small snippet, code snippet, where we have declared some shared counter variable, a variable. You can say like we have declared some integer variable which is initialized to 0, and we have two tasks. Okay, two tasks are created. Task 1 is created here, and task 2 is created here, and both the tasks they are accessing the same variable. You can see that. So task 1 is also incrementing the same variable, reading, incrementing, and writing. And task 2 is also performing operation on the same variable, that is the shared counter plus plus, right? So both the tasks trying to access the same resource or same variable. Then what happens? A conflicts will happen. Okay, like a race condition will happen if both simultaneously tries to access that. Okay, so the problem is non-atomic operation can be interrupted. So non-atomic, nothing but, see, when the operation is happening at that time, interrupts are not allowed. So somebody else cannot disturb. Then we call that operation as atomic operation. If something is happening and somebody is disturbing, able to disturb that, then it is non-atomic. Okay, non-atomic operation. Okay, so this results into race condition, and to overcome the problem of this race condition, we can introduce the synchronization mechanisms like semaphores and mutex concepts. Okay, that we are going to discuss. Right. Now coming to here, critical section. See, one more point is added here, critical section. So code segment that access shared resources and must not be executed currently by multiple tasks. That means some shared resources are accessed, but not at the same time by multiple tasks. Okay, so critical section. Okay, so what is the solution for race condition? See, first thing I said, what is a need? What is a need for synchronization? The need for synchronization is, the problem is race condition. To overcome the race condition, we need synchronization. So what is synchronization? They have introduced some mechanism to solve that race condition. And what mechanism? So that mechanism is nothing but the concept of semaphore, the concept of mutex. Okay, so here, uh, integer variable with atomic operations. Just think here, like the same integer variable, it is updated by both the tasks, but the operations are atomic operations. They are not non-atomic. Atomic means when one task is updating a value to the variable, the other cannot enter there. Okay, until it finishes. Okay, so that is nothing but atomic operations. Okay, then yeah, of course this is invented by this person in the year 1965. So here two main operations, wait and signal. Like if somebody is doing something, then the other task has to wait until it gets the signal from that task which is already doing some operation on that particular shared resource. Okay. So let's see some examples. See here, again, I have shown some snippet like here, wait for semaphore. So now again, you might feel like, what is semaphore? Semaphore, it's the name they have given for this concept. You can call this as a bucket and key concept. You can, in simple words, you can say like it's like a key. Semaphore is like a key. You have a key. Whoever has the key, they can use the room. Okay. So get the key, use the room, and put back the key, return back the key. That's it. That's the concept. The concept is very simple. Like task one, task two, both wants to use the room, and we have one key. Let's assume we have one key. Whoever gets the key, he will use the room. And until he returns the key, other task cannot use the room because there is no key. There was only one key that has been taken by task one. If task one returns the key
Sir, I
after
have a
using,
question.
yes, yes,
Hello, sir.
yes.
Like semaphore allocation, is it based on first come first serve basis all the time, or can we assign the priority to the task, like wherein it can interrupt the lower
Correct.
priority
It
task? And
depends. Correct, madam. It depends on the priority of the task. Like scheduler, who is scheduling the task? Scheduler. Okay. Now
okay,
you have assigned the priority to the task. Like you have created some 3 4 tasks. Okay. And you have assigned the priority, and you have given that task to scheduler. You are telling scheduler, take this 4 tasks, you schedule it. Now again, scheduler is following which scheduling algorithm? Again, we have so many algorithms. Okay. So there we have first come first serve algorithm. Okay. We have least execution time algorithm. There are so many algorithms, but majorly in real-time operating system, the type of scheduling algorithm that is preferred is priority based algorithm with preemption. Preemption. Okay.
okay.
Priority
But
and
while
preemption.
using the semaphore, we also go with the priority inheritance. Like
Yes.
just because it automatically deals with the main problem with the semaphores is priority inversion. So we'll go with the inheritance. So in which kind of RTOs, is there any particular kind of RTOs
Actually,
wherein?
actually, that priority inversion and priority inheritance is supported in mutex mechanism. It is not supported in semaphore mechanism.
Okay,
Okay.
okay. You mean
So
to say mutexes are a
yeah.
kind of semaphore wherein it automatically deals with the inversion?
See here, I have added the differences. You can just check here. Like priority inheritance supported by mutex, and it is not applicable in binary semaphore. Okay.
Okay, sir. Thank you.
Yeah. Okay. So I was just talking about the snippet. Like we have the key. So until you get the key, wait for the key, wait for semaphore. Let's say this task is waiting for semaphore. Once it gets the semaphore, do the operation and return the semaphore. Like in terms of number, okay, in terms of coding, you can say like semaphore is a value. You can say like a value. You have that value signal. Let's say the count is 1. Okay, if you have the count 1, you you just check whether the count is less than or equal to 0, then keep waiting. If the count is more than 0, like there is a value, there is a key, then just you decrement and you start doing your job, so that when the other task, if it wants to access the resource, it has to acquire the semaphore. Then it will see like, okay, semaphore value is 0, like I don't have the key, so somebody should make it 1, then I can decrement and I can do my task. Okay. So it's all about the concept of key bucket and key concept. Just take the key, do your job. Until the key is available, the other person will be waiting. So like this, you can bring synchronization between 2 tasks. Okay. So that the shared resources can be managed effectively without creating the problem of race condition. Okay. Conflicts. Okay. So coming to types of semaphores, we have 2 types of semaphores: binary semaphore and counting semaphore. Okay. Now again, I can explain you this in a simple way. Like you have one key, only one key, and 2 tasks. So both the tasks wants the key. Whoever gets the key, he can use that resource, and other has to wait. Okay, let's say binary semaphore is one key concept. Okay, counting semaphore is like multiple keys, multiple tasks. Let's say you have 10 tasks and you have 5 keys. So at a time, 5 tasks can run. At a time, 5 tasks can run. Why? Each task can take one key, 5 keys are available. So if 5 semaphores are taken, then 5 tasks can run. But total you have 10. So out of 10, 5 can run, 5 will wait until somebody put back the key, until somebody gives that semaphore, right? Okay, now coming to binary semaphore, I said one key, only one key. So here counting semaphore, more than one key, value 0 to n. So there's 0 or 1. Okay. So now coming to here, mutex. Again, we have another mechanism called mutex. So mutex is similar to binary semaphore. Like we say, like mutex is same as binary semaphore because there also we have just one key. Let's assume one key, or it's a kind of locking and unlocking mechanism where the count is one, again one, the value is one only. So whoever acquires the mutex, he can use the resource, and then once he releases the mutex, other can acquire the mutex and then he can use it. It's like just one key concept again. But you might question, like, then why the name difference? Why binary semaphore concept? Why mutex concept? Right? See, when they are saying there are two different concepts, binary semaphore and mutex, and we are telling that binary semaphore is similar to mutex. When it is similar to mutex, then why we have to call it as mutex, and then why we have to call it as binary semaphore, right? So here there is small difference. So the small difference is in semaphore, let's say you have taken the key of the room and you have used the room, but you did not put back the key. You took the key away with yourself. And somebody else coming and putting the key back. That means it is not mandatory that the person who has taken the key here, he should only put back the key there. It's not mandatory in semaphore concept. Okay, but in mutex, it is not like that. If you have taken the mutex, you should only put back the mutex. Nobody else can put back that. That means you have taken the key, you have used the room, you did not put back the key, you left with key. And other person was waiting for the key, other task. But where is the key? You took the key. But somebody else, let's say the owner of the room, he brought and kept one more key there. You can use it. Just I'm giving example. Okay. So that works in semaphore, but that is not the case in mutex. Okay. So in mutex, what happens? In mutex, it is like if you have taken the key, you should only put back the key. That is the decision. That's the mechanism. Okay. That's the difference between binary semaphore and mutex. And we can call that both are similar. Why? It's a one key concept. Both are similar. Okay. But the difference is who will put the key back. That creates a difference between binary semaphore and mutex. Coming to counting semaphore, as I already said, you can have more than one key, and whoever gets the key, they can use the resource, and others will wait. And that works with that concept. Okay. Now again, let's say you are giving two keys, two person, one room. Again, there is a clash. Again, there is a race condition. See, if you give one key for if you keep one key for one room and two person, then you can use semaphore concept. Whoever takes the key, use it and return it. But you have two keys, two persons and one room, both will have the key to open that, use that. Again, conflict will happen. Again, race condition can happen. You can't say like I avoided race condition using counting semaphore. So again, it depends on how many keys, how many resources. Okay, so that thing has have to be understood. Okay, so uh, these concepts or these mechanisms they have brought for overcoming the problem of race condition, especially in multitasking environment like real-time operating system. So for that, we are calling that as synchronization mechanisms. And these synchronization mechanisms, nothing but the semaphore concept in that binary semaphore, counting semaphore, and then the concept of mutex. Okay. When it comes to interrupt is again different. Task task is different, interrupt is different. Okay, so you have created multiple tasks which are running in the system and they are scheduled by the scheduler. But interrupt is something which is an external request coming from external device. In between, let's say your processor is executing multiple tasks simultaneously. RTOS, your RTOS is handling multitasking. It's multiple tasks getting executed in your processor. Meanwhile, somebody has pressed some switch on the system. That means some interrupt occurred. That how that interrupt is handled when it is already managing multiple tasks, right? So let's say some high priority task is already under execution and there are already some tasks which are lined up. Okay, and meanwhile interrupt occurs. So there the scenario will be different. Okay, that is nothing but your interrupt context switching. Okay, so context switching between the task and context switching from task and interrupt, that is different, right? Okay, so you can see here, just for better understanding, I am showing you this diagram. Like we have two tasks, producer task and consumer task. So producer task is giving the key and consumer task is taking the key and it executes. Okay, like somebody has to give the key, somebody has to give the semaphore. Semaphore, we are calling it as key here, right? Okay. So once the key is available, the other task can take and perform its operation and then it can give back. Okay. Or somebody else can give back. But that is not the case in mutex. Who has taken, he should only put back in mutex concept. Okay. So one more diagram I'm just showing for you to have clarity on the concept of the semaphore. Like you can see, producer is giving three semaphores, three keys. Let's say producer is giving three keys, semaphore 1, semaphore 2, semaphore 3, and there are three consumer tasks, task C task 1, C task 2, and C task 3. And let's say C task 1 wants to use the resource, okay, and C task 2 also wants to use, and C task 3 also want to use. So at that time, all should have the key. If only one key is there, or at a time one consumer task can use that. Okay, if you have multiple keys, that means this is the concept of counting semaphore. I said you can have multiple keys with multiple tasks, and every task acquires one semaphore, they can utilize that resource. Okay. Okay, so just now we have had a broad understanding of synchronization mechanism, the concept of semaphore, binary, counting, and mutex. So we'll have a quick difference between mutex and semaphore. Okay, and also I think uh, previously one of the professor raised a question on priority inheritance and inversion. Okay, so I will just add some point on this anyway. I will just add some information on this and also will add some information with respect to ISR versus task context, right? Okay. Here, okay, so I'm just showing some RTOS code, embedded C code, which is using free RTOS APIs. Like you're bringing free RTOS APIs, nothing but you're combining free RTOS operating system files with your application program, nothing but your multitask programs. You're creating multitask using this RTOS APIs, and then you're running those multitask, managing those multitask, handling those multitask with the help of the features of this real-time operating system. Nothing but kernel, and kernel has all those features which will take care of uh, scheduling, task management, inter-process communication, share shared resource sharing, okay, and synchronization, interrupt handling, etc. Okay, so just quickly look at the differences. So ownership, mutex. So that's what I said. Ownership in mutex, it is there. Only owner can unlock. Like whoever has taken the lock, he has to put back the key. Okay. Whereas in binary semaphore, there is no ownership. If somebody has taken the key, somebody can put back the key. So there is no ownership. And priority inheritance is supported by mutex, but it is not supported by binary semaphore. And recursive locking, that is possible in mutex, but it is not possible in binary semaphore. And use case, this is mutual exclusive, and this is normally signaling and synchronization. So ISR usage cannot be used in ISR, and we can use binary semaphores to signal for signaling. We can use binary semaphores for signaling in ISR, inter-service routines, right? Okay, so priority inversion. Just quickly, I will add some information. Let's say you have some 3 tasks which are running in your system: highest priority task, medium priority, and low priority. So let's say your high priority task is blocked because the low priority task is acquired the mutex. Let's assume low priority task is taken the mutex and it is running, and high priority task came, but it cannot get the CPU. Actually, scheduler. See, the job of scheduler is whoever has the highest priority, immediately what scheduler will do, it will stop the low priority task. It will give the chance for the high priority task. That's how scheduler schedules. Okay, in preemptive scheduling, priority based preemptive scheduling. But the low priority task has already taken the mutex, the lock or the key, and it is running. High priority task came. At that time, scheduler cannot schedule the high priority task. The reason is the high priority task need the mutex, the lock, the key. So where is the key? The key is with the low priority task. Then how high priority task can get the key? It cannot get until low priority task put backs the mutex or releases the mutex, unlocks the mutex, right? Okay, then this is a challenge. Then what happens if this is happening? Meanwhile, let's say some medium priority task comes, gets scheduled. Okay, some medium priority task comes, it gets scheduled. High priority task is blocked because it is waiting for the mutex from low priority. Immediately, medium priority task comes, and medium priority task doesn't need mutex. Without mutex, it just wants to execute. Then scheduler will give chance for medium priority. Even though high priority is waiting, chance is given to medium priority. Why? Medium priority does not want the lock, the mutex. It just wants to execute. Then what happened? High priority task went into starvation. Like high priority task is just waiting, starving, and medium priority task is coming, executing. It is preempting the low one, executing. Again, the low one is occupying the space because the low one has not written the mutex. Okay, so that's how this scenario will create a problem, and we call that problem as priority inversion. Okay, then what is the solution? So the solution is priority inheritance. Like temporarily boost low priority task to high priority. Let's say low priority task is already taken the mutex and running. And if high priority task comes at that time, chance is not given for high priority because high priority is expecting mutex, but mutex is with low priority. So at that time, if medium priority comes, then chance is given to medium because it doesn't want to use mutex. So that is priority inversion. To overcome the problem, they thought of some solution. What is the solution? The solution is like, why can't we increase the priority of the low priority task when it is running and it has the mutex, so that if any medium priority comes, it will not be given chance, so that the low priority will complete, it will release the mutex, and immediately the mutex is taken by the high priority, and high priority will come into action. So the problem of priority inversion gets solved. Okay, so that is supported in mutex, but that is not supported in semaphore. Okay, so ISR versus task context. So what you should not do in ISR and correct ISR pattern. See here, let's say your ISR is taking semaphore, and then see whenever ISR interrupt occurs, just think like whenever interrupt occurs, context switching will happen. Your processor will jump, give the priority to interrupt. Interrupt has the highest priority. Let's assume it is already running some task, but because of external interrupt, it has switched from external interrupt to ISR. Okay, because interrupt has the highest priority. Okay. When it shifted there, then the interrupt has taken the keys and then it started doing heavy processing. Now what happened? Your processor is fully occupied by only interrupt service routine, and all other tasks which are scheduled, they are waiting, they are starving. Like some tasks, they are critical. If they don't get executed, a system crash can happen. But your processor is busy in servicing the ISR. Why? ISR has taken the keys, it's not releasing. Okay. So this is not suggested in real-time operating system, or this is not allowed if you want your task to be taken care within time constraints. Okay, this is something wrong. Okay. Whereas what can be done, immediate switching can happen from your task to interrupt. And in interrupt, the interrupt has to give the key for some other task and tell some other task that my job you do, I have informed. Like the processor switched from task to interrupt, and interrupt gave some signal to another task, brought another task into action, and said that I have waked up you. You become part of the other task. Scheduler will be scheduling you also, and my required job will be done by you. That is called as deferred work. We call it as the concept of deferred work. In interrupts, we have the concept called as top half and bottom half. So usually we don't discuss this top half and bottom half concepts in interrupts. Uh, we normally talk about main program and ISR. Just the interrupt, whenever interrupt occurs, the control gets transferred from main to ISR. After servicing ISR, it comes back to the main. This is what we generally discuss. But there is a deep concept called top half and bottom half for interrupt handling, so that in real-time operating systems, so whenever there is a quick response required, it will jump to the ISR, but remaining job of the ISR will be performed by another task because the interrupt will enable another task. So that the task becomes part of the other task, and then it gets scheduled based on the priority by the scheduler, and everybody will get the opportunity in real-time operating system such that all tasks are managed effectively within time, and that will result into a real-time management, right? Okay, this is correct ISR. See here. Semaphore given from ISR. ISR is waking up, giving a key for some another task who is waiting, so that that task comes into action that will take care of the job which is required to service that particular interrupt. Okay, and that means it is yielding the processor. It is not holding the processor. It will yield the processor. Yield means it will release the processor so that processor can take care of all other multitasking. Okay, so that every task gets opportunity based on their priorities, and the system manages everything in real time by executing all the multitask. Okay, so I have listed some use cases here. You can just look at these use cases. So I have taken automotive as an example. Okay, engine control, sensor fusion. Okay, engine control use case. So you can consider as engine control use case where sensor fusion and actuator coordinating problem. Okay, that means multiple sensors, they are producing data asynchronously, and task reading sensors may override shared data before. So here, just imagine like you have a memory, and that memory is shared between multiple tasks, and every task is getting data from different sensor. Let's say task 1 getting data from sensor 1 and putting in the same location. Task 2 also getting data from the same location and putting task 2 is getting data from sensor 2 and putting data in the same location, and task 2 getting data from sensor 3 and putting in the same location. Now what will happen when that same location is shared between the task? If you are not bringing the concept of synchronization, if you are not bringing the mechanism of semaphore, if you're not bringing the concept of mutex, what will happen? Then the race condition will happen. The results will be unexpected. The behavior will be unexpected. The outputs may be unexpected. Okay. So to make sure that the data is not overwritten by another task before the data is actually processed and the decision is made. Okay. So at that time, the concept of the semaphore is required. Okay. So you can relate, you can link that. So already we discussed, you can just relate. So we can bring the concept of binary semaphore, which is used for signaling. Like task one will take the key, complete the job. Then task two will take the key, complete the job. Then task three will take the key, complete the job. Okay. Another use case I'm showing, advanced driver assistance system ADAS, where we have data coming from camera and radar fusion. And these same thing again, I can say like shared buffer, like both the tasks which are used here for these sensors, they are getting data from these sensors and they are putting the data in the shared buffer. Okay. And there are chances of risk of overrun or underrun if synchronization is missing. So of course they are bringing the concept of counting semaphore. Actually here a pool of fusion buffers is created. A pool of fusion buffers is created so that it can, a fusion task will update data in the fusion buffers. Okay. And camera will update in those fusion buffers. Like we have a pool of buffers. When the buffers are full, then overwriting should be avoided. Okay. Until the buffers are available, then both can keep writing in different buffer areas. Okay. So that will not result into overlapping. So instead of bringing binary semaphore, you can bring counting semaphore concept here. And one more use case, like in vehicle infotainment, like you have a shared display resource, like you have in car dashboard, you have that display uh, display area, okay, which is displaying the information to the driver, like navigation information, rear camera or media player. So which is need to be updated in the infotainment display. So that infotainment display, it might be a shared resource between multiple tasks, like different tasks using the same display to update their sensor information. So at that time, to avoid the problem of you know screen flickering or inconsistent user interface, so you can bring in the synchronization mechanism, that is mutex locking and unlocking mechanism, so that the task one will lock, it will display its information, then it will unlock, and then the task two will acquire the mutex, then it will display, and then it will release the mutex or unlock the mutex, right? So where mutex is also the mechanism which supports the priority inheritance, that it overcomes the problem of priority inversion. Okay, so that is about the concepts we have discussed, and I think we have a few more minutes, some 10 minutes. I can just quickly run and show one example on mutex. So I have ready-made code. I'll just run and show you that. Okay, just for practically connecting how things work there, and yeah, of course. So before I go there, you have any questions? Anybody there? You can ask those questions. Okay, so just you can keep posting your questions in the chat, or you can ask in between. I'll just quickly open this Ubuntu app and quickly just show you one example with race condition. uh, what is your output, okay, when you have multiple tasks, multiple threads. So how this race condition is happening, and what is the expected output and what you are actually getting. And if you bring mutex to solve that problem of race condition, then are you getting the actual expected output? Just two programs I will quickly run. It will not take more than 3-4 minutes. Okay, so already I have the code with me. Just you need to connect the concept what we discussed. Okay. Okay, so I'm opening this Ubuntu app. Okay, so here I have one folder. Okay, I'll just get into some folder FDP. So you can see I have some C file already written, using multi-threading POSIX multi-thread library, created some two threads, and both the threads trying to access the same shared resource, and they're trying to increment the same variable. Okay. Okay. So just quickly show you the code, and then we can run this. Okay. So cat race.c. So you can see here, this is the code. Like we are creating number of threads true at 2, and we are defining like number of increments. So for loop, like I'm going to write a for loop of which is going to repeat 1 lakh times. Okay, the count. Okay, a macro is defined, right? So we are declaring some variable. See, this is the shared variable, shared counter variable, and here we have written one function, increment counter function. So whichever thread gets the semaphore. Okay, we have not introduced semaphore here. We'll introduce in another program. Here, let us assume we have one function. In whoever executes the function, we are going to create two tasks, two threads. So whoever gets the opportunity to execute this, okay, so it will execute this function where the loop will repeat 1 lakh times, and the counter value should reach to 1 lakh. Okay, then coming to main program, you can see here in main program we have created uh, how many threads, number of threads, 2 I have given. Using pthread create, we are creating 2 threads. Okay, these are the APIs we are using, and the syntax and all you will find in the documentation. I'm not going right now into more into details about this part. Just think like this part will create 2 threads and 2 tasks, 2 tasks, 2 threads, and both the tasks trying to call which function here. This same function, increment counter. Task 1 also tries to access that, and task 2 also tries to access that. So then if both access this function, if the function increments the counter 1 lakh times, if task 1 executes 1 lakh time and task 2 executes increments to 1 lakh, so 1 lakh plus 1 lakh, we should get 2 lakh. That is the count what we are expecting, right? So let us run this. So here I just want to run and show you what is the result because of race condition. We are expecting 2 lakh to be the counter value. Okay, count value. Okay, so let us compile this. This is the, okay, I think I have already compiled. Yeah. So the output, I'm just getting the output file with the out name, and I'm compiling with linking the pthread library, and this is our source file with the multitasking and using shared resources. Okay, I'm just compiling this, and I got out file here. Okay, let us run the out file. So /out. So execute. So do you see here what is the count we are getting? It is 1,20,000 something. Actually, our expectation is 2 lakh, because if task 1 executes that function, the counter value should become 1 lakh because the loop repeats 1 lakh times and incremented 1 lakh times. And if task 2 also executes that, then again 1 lakh times. 1 lakh times plus 1 lakh times, the count should be 2 lakh. But because of race condition, what happened? So when both went to execute the function, one that execution, like somebody is winning, somebody is losing at the same time. See, both are running to get the chair. The one who got, he will sit. The other one who got, he will not sit. Okay, like that. So in that race, what happened? The count is not properly getting updated because of race condition. And instead of 2 lakh, we are getting 1,20,000. This is your race condition. Okay, now I will quickly take the code where we have brought the concept of mutex. See here, fix the race condition. Here we are bringing the concept of mutex. So if you look at here, we are creating one pthread mutex, counter mutex. Okay, so whoever comes to this function, they have to lock the mutex, lock that variable, increment and unlock. See, locking and unlocking mechanism is written here in this part of the code in the function. Whichever task executes this function, first it will lock, it will increment, then it will unlock. Okay, so then what happens here? The race condition will get avoided. Okay, let's get this code. So this code has the concept of race condition. So here I will create one more file, nano. race underscore fixed. Okay, fixed dot c, and I will paste the code, exit from here. Now we have two files. One is a file with race condition, another file where the race problem is fixed with mutex concept. Okay, now let us compile and run this. So I will compile race underscore fixed. Okay, now I gave the same name out. I could have given a different name. Okay, let's have two different files. So this is out for race condition, and I will give out1, the output file name as out1 for race fixed problem. Okay, so now if you check, we have two output files. Out is for with race condition, out1 the race condition solved because of mutex concept. Okay, let us run this dot slash out. So out, it will give race problem. See, because of race problem, it's not 2 lakh, count is not 2 lakh. Race, okay, dot slash out1 with mutex. So with mutex, what is your answer? 2 lakh. That means the problem of race condition is solved here. Okay. So you can bring such hands-on examples when you're bringing those concepts as part of your syllabus. Okay. So I think we are at the end of the session, and you guys, any of you have any questions, we can take it forward. Yes. Any questions, guys?
Hello. Hello.
Yes, yes, yes.
Dear participants, if you have any queries, this is the time to get the solution for your queries. Any questions from the participants?
No questions.
Yeah,
No
thank
questions.
you.
Okay.
So I will stop here screen sharing.
Yeah, Mohsin.
Thank you all of you for your patience, and also, and thank you for being part of this program. Okay, so it's my privilege. Thank you all of you for the organizers.
Thank you, Mohsin sir.
Yeah, thank you.
Okay. Thank you,
So-
sir. Dear Mohsin sir, on behalf of all the participants and the organizers of the FDP, I would like to extend our sincere gratitude to you for your insightful and engaging session. Your presentation was not only informative, but also highly inspiring. The clarity with which you have explained the complex concepts and the practical perceptions you shared added a great value to our learning experience. It was truly a privilege to benefit from your expertise and depth of knowledge. Thank you once again, sir, for taking the time to be with us and for contributing to the success of this FTP. Thank you.
Thank you. Thank you. Thank you very much. Okay,
To
so I
start
can
the
leave.
next session, may I now request Ashwini SS, Associate Professor in the Department of ECE, to take over the session. Ma'am?
Am I audible?
Yes, ma'am, you are audible.
Yes,
Okay.
madam.
Okay, sir has joined. Anuprasad, sir.
Yes, ma'am. Am I audible?
Okay, sir. Yes, sir. Okay.
Yes, sir, you are audible, sir.
Sir, let me introduce about yourself. Okay, sir. I'm going to introduce. Good evening, everyone. It's a pleasure to have you all joined here today for the third day online FDP on advanced embedded system, RTOS and automotive CAN applications. We are honored to have you with us, Mr. Manu Prasad, who has graciously agreed to share his expertise with us. Senior Director, Tech Strategy Team, Samsung R&D, Bangalore. Accomplished software engineering leader with 27 years of experience in network and mobile software development across diverse technology domains. Currently serving as the head of Tech Strategy Team at Samsung Research, Bangalore. Driven by a passion for open innovation and university industry collaboration, built and successfully scaled programs such as Samsung Prism, Samsung Seed, and also played a key role in establishing the flagship Global Citizenship Program, Samsung Innovation Campus. Driving organizational transformation through AI or generative AI tools, privacy, preserving data at scale. Expertise span across multidisciplinary functions like project management office, data privacy, IT infrastructure management. Renowned to create customer centric solutions, proven track record in building, mentoring, and leading high performance teams. Today, Mr. Manu Prasad will be sharing the significance and the need of CAN architecture and arbitration, which often incorporates mechanism for efficient message prioritization and arbitrations, ensuring reliable communication even when multiple nodes transmit simultaneously. Please join me in giving a warm welcome to Mr. Manu Prasad, sir. Sir, the session is over to you.
Thank you, ma'am. Somebody can allow me to share my screen. That's one. I think, ma'am, there is some confusion in the agenda. My topic was slightly different. I had communicated to Komla, ma'am, that there will be a difference in the topic. Is that okay if I
Okay,
talk
sir.
about the embedded system? Yeah.
Yes, sir. You can talk about the embedded system. Okay, sir. You can start with your presentations.
Is my screen visible? Somebody can confirm.
Yes, sir. Now it's visible, sir.
Your screen is visible.
All right, one second. Give me a moment. It's good?
Yes, sir. It's good. You can start.
Okay, thank you very much, ma'am. Good evening, all. Today, for the next maybe 45 minutes or 1 hour, I'll be talking on the design challenges in embedded systems. Because we know what is an embedded system, why is it important. So I'll not touch upon those aspects, but I'll talk about challenges, what is faced when we design it, and how hardware, software, and system integrations happen. See, one of the popular embedded system is the mobile phones, right? So today I'll dissect the mobile phones. Mobile phone is, of course, an embedded system because it's a specialized computer system designed to perform some dedicated functions, right? That's pretty much the definition. So I will walk you through what mobile phone contains, what it goes in, what will be the size of software, etc. This is our day in and day out device, right? I mean, if it doesn't work, it's almost like we are handicapped. So I thought this is the case study which is good for all of you to understand and appreciate what goes in making one embedded device. So as I said, so I'll be dissecting this entire mobile. This is our Samsung Galaxy Fold 7. So which has got a dual display. It has got display both on front and back. So I took this because in the market, this is the latest and greatest device. So looking into this device made sense to me. So any questions so far before I get into the topic?
Any question from any participants? You can unmute your mic and you can ask. Any questions? Sir, hope there is no questions. You can continue, sir.
Okay, thank you, ma'am. If there is any questions, you can keep putting in the text box so that I can answer later as well. No issue. So let's get into what we call as Galaxy Z Fold 7. Whatever I speak today is predominantly in the open thing. So there's nothing confidential. Whatever I say is my experience. So I'm not going to divulge any confidential info as far as I know. How many of us really think, when we buy a phone, do we really go through the specifications or not? Do we really understand this one device which is in our hands, pockets, bags? Now, how complex is it? What it contains? Every day morning, I think most of us use this from alarm, right? We wake up with this device until the end of the day. You use it for your sending emails, text, watching videos, entertainment, gaming, etc. How much this one small device can take it, right? When we do this design of this embedded system, a lot of things go through it. It is not a simple device which can be done by anybody. To be honest, in India, still we do not have a technology. I'm talking about India as a country. We do not have a technology to even make one smartphone as by ourselves. We always have to borrow technology from other countries. That's the state of affair. But today I will explain what this embedded device, this mobile phone contains. What are the different challenges we need to consider when we are designing one particular product, etc. So I have taken the highest configuration, but if you see that we have other M series and A series, which is a shorter version of this product. So this Galaxy Z Fold 7, this is a 8-inch device with two like 1968 into 1968 pixel display. The camera is about 200 megapixel. Whatever picture you can take a picture of 200 megapixel. Of course, the memory will get used faster, but the capacity is 4K image to 200 megapixel you can take. The RAM, what it comes is either 12 GB RAM or 16 GB RAM, and the battery is 4400 megahertz with 25 watt charge. Why I'm saying all this is, any embedded system design engineer has to know when he writes program, what is the memory, what is the power he can use, etc. So this is just around 200 grams and 4.2 mm thickness, very small, if I can say that. Roughly this costs around 1.5 lakhs in the market. So that's the cost here. So what does a mobile phone contains? You might have heard this. I'll go one by one, right? A network, right? It has to, whenever you want to make a call, you need to have a network. There is different generations that it has to support. It has to support 2G, it has to support 3G, it has to support 4G, it has to support 5G. Why I'm saying all this is, this phone can go anywhere in the world. Depending on that country, what kind of network available, this phone has to support. So imagine the complexity, right? One device, any band, anything it needs to address. So that's why network is very important in this embedded device, and basic phone means network is needed. So that's why it's critical. Next comes the body. I will skip the body part because not much of importance here. However, one important part is the I'll skip SIMs. What kind of SIM it supports? IP48, is it? One second. Whether it is waterproof, dust proof, etc. So I'll not get into the mechanical aspects or the hardware aspects. I will try to keep it from a software perspective as much as possible. Then it's all about the display. As you know, first, if somebody wants to buy any phone, first what they check typically is the camera. Second is the display, how good you can see. So whether it is AMOLED, how much is the refresh rate, etc. So what is seen is, bigger the display is better. People like it because they can see movies, and the better the refresh rates, it's the viewing experience is better. So that's important. The next important part is the platform. Basically, this is an Android platform which comes from Google, Android 16. And on top of it, we do add our OEM code, whether it is Samsung or anyone else for that matter. We add our own code, our own UI layers, etc., so that it's ours. I will talk about this Android a bit later as well, but it's an Android 16, the latest part. The heart of this device is this Qualcomm chipset, the Qualcomm SM8750. I will walk you through the spec as well. This is the core. One point of time, there used to be two main chipsets in a phone. We used to call it as AP, application processor, and communication processor. Now, these days, the high-end chipset comes with a single processor. It can handle both the modem aspect as well as the application aspect. Mind you, this is 3 nanometer. Okay, 3 nanometer, which means so much transistors we can load into this chipset. It's very thin and it can do so much compute. It's an octa-core thing, and we have a GPU here, Adreno GPU. For any of your AI/ML, if you want to run your models or anything, there is a GPU here. Memory, card slot is not there, but the internal memory are there. Why I'm saying this is, when I start going into the challenges, this becomes the trade-off point. So that's the reason I'm just giving a bit introduction, which may be boring, but please bear with me. The internal memory, as you know, it's two types. The RAM, that's when you want to run a program, RAM is important. And other one is the storage, where you want to store some persistent data. Camera is important. You can see that there's 12 megapixel camera, 10 megapixel camera, 200 megapixel camera. So people, when they open the camera app, they can set appropriately. Of course, whether you need a wide angle, tele, or ultra wide, there are different types of lenses. This OS is the optical image stabilization. This is the zoom, the optical zoom, the hardware zoom. So if you ask me software wise, what is the most complex? It's the camera. And if you are recording a video, it's 8K video, you can record at 30 FPS, 4K video, you can record at 60 FPS, the HD 1080p, you can record at 60, 120 to 40 FPS, etc. So this is the video capability. In phones, we have two cameras, as you know, the back camera and the front camera. Front camera is, we call it as selfie camera. So I'll skip on that. Selfie camera capabilities will be slightly lower than the main camera. Sound, I will skip, not much important today. The other one is the communications. We need to support a lot of different type of communications. One is the WLAN, Bluetooth, the GPS for positioning, NFC, radio we don't have. These days we don't support radio. Previously we used to. The USB-C type. So these are supported. Next is sensors. There's a lot of sensors. Fingerprint sensor, accelerometer, gyro, proximity, compass, barometer. You can just see how many sensors is loaded in one small device. UWB is supported. Samsung DeX I'll skip. Battery is 4400. You know that once you charge, it should last for at least 1 day. Now you need quick charging, etc. There are other miscellaneous things. This SAR is the radio thing. So I'll come on that. I have one more slide. And there's a lot of test benchmark. So this is the specification of the device. As you can see, this phone, many times it beats the capability of a desktop. So that much is packed. The source code roughly is around 250 million lines of source code is packed in this phone. Let me repeat, 250. In that will include around 100 million comments, etc. But source code, pure source code, whether it's Java, Python, etc., is more than 100 million lines of code. 1 million is 10 lakhs. So 10 lakhs into 100. So maybe 10 lakh crore lines of code is what this embedded device has. So that's the complexity. So when we are making a software for one particular device, this 1 lakh plus, 10 crore plus lines of code has to be handled without defects. Okay. So that's the complexity. It's, let me tell you, in my experience, it's very complex. Sometimes the RAM image, not RAM image, but the binary download, it will be around 24 GB binary download itself. That is the maximum capacity of download. We have, for a smaller models, we have 18 GB, etc. But this roughly is around 22 to 24 GB. That's the binary size after you build the code. So that's the thing. This is what I can say, some basic architecture. This is kind of old architecture, but there's much more complexity. In terms of simplification, we have the OS, we have the libraries, we have the Android runtime, we have application framework, we have applications. So I'll not go into this, but just to give an idea about how it's structured in a layered architecture. I would like to Is my screen still visible?
Yes,
Is
sir,
my-
it's visible. Visible, sir.
Okay, thank you. See, I want to go into this Qualcomm chipset. You can see that Qualcomm SM7850, right, ma'am?
No, sir, your presentation first slide is visible.
Okay, just give me a moment, please. Now, ma'am?
It's visible, sir.
One second. Okay, Qualcomm 8750, because this is the heart of this device. So I would like to go through what it primary contains. They call it a Snapdragon. That's the thing, and it's a 3 nanometer, 8 cores, 8 threads. So each core will have 8 threads. Base frequency is 3.53 gigahertz, and turbo frequency it can go up to 4.4. So these are the important. Cache memory is 24 MB, and GPU is F. If you consider the floating point 32, it is 3.3 giga flops. For gaming, graphics, DSP, display resolution. So just setting the context, how complex is this chipset? Okay, all right, I'll come back to my slides. Okay. All right, ma'am, can you see my slides? Somebody can
Yes,
confirm.
sir. It's visible, sir.
So far I gave an introduction about what a hardware looks like. So that complex hardware, let's get into the design. When we are writing software, what we need to consider, etc. Since I think every one of you are using phones, I'm sure you will be frustrated if you try to make a call, the call doesn't connect, or you try to scroll something, it is not thing. You press a button, it doesn't respond immediately, right? I think you would have seen at some point of time, etc. All this either in your old phones or etc. So when we do a design of this phone, three things are very important for us. One is the performance. So whatever we do, the user of our phones should not feel it's slow. Okay, so that's one thing. Second, power. it should not drain. I can write and make my clock speed go high, give a faster, but it should not drain my battery, because people don't carry their charger always. They charge in their home, go to their office, wherever they want, but it should at least last. So there is always a trade-off between the power and performance and power. These days, a lot of apps consume, not just as the OEM, but even third-party apps consume a lot of power. So we need to have some, monitoring systems. If some app is using too much of a power, notify the user, etc. A lot of young people use this gaming. So this gaming also, it should support multimedia. Like, people like to watch hours of video on the phone, right? So those sort of things also it should support as much as possible. Also, as a manufacturer, what we try to do is keep the phone thin as possible. Meaning, the thinner the hardware is, the thermal constraints starts kicking in. The device will start heating, etc. So we need to be very, very cautious about that. So that the device is not getting heated, and there is this balance of peak performance versus battery longevity. So these things is in our back of our mind. Power management. We know, you cannot put too big battery; it becomes bulky, right? We have to choose the components very nicely, so that we use the right balance between those two. As I said, people prefer slim phones, so it's very challenging to have slim designs, because how do you do the heat dissipations, etc. The people expect all kinds of feature on their phones, whether they use or not. They would like to have this also, that also, those, you saw all those sensors. The PCB should be able to accommodate so much, right? If you are going for 2G, 3G, 4G, 5G, the communication things, the antennas can vary. You have different camera modules, so many settings, so many sensors there, etc. So this heat is very critical. We have many algorithms to manage this. We have threshold settings. For example, if it goes beyond 40 degree, we throttle the performance, etc. All this requires a lot of testing, by the way. So that's one critical piece. Bringing so many items together, making it work. Make sure heating is under control. Make sure zero defect is very critical in any of the phone manufacturers. So I'll just skip this. There are a lot of things which goes into hardware, so I'll not get into the hardware. This is mainly the surface temperature. How do we manage the surface temperature? How to keep it normal so that it doesn't burn your hand or or your pocket. Coming to connectivity, as I told you, we need to support from 2G, 3G, 4G. It should support Wi-Fi. Wi-Fi also has got different bands: Wi-Fi 4, Wi-Fi 3, backward compatibility. Bluetooth also, you have different Bluetooth profiles. BLE, also low energy Bluetooth also we need to support. It should interoperate with different kinds of the Bluetooth headsets. If you have, it should work. It's not just it working only with one particular device. It should work with the entire set of vendors or the equipments in the market. NFC we support so that you can communicate. The GPS we need to support, because that for any map or anything it should work properly. So having so many antennas, then interference management among these antennas, global frequency band compatibility, these are some of the challenges we need to consider when we are trying to do the design of this phone. So I will take a pause here. So any questions so far? Let me see, where are the questions? Any questions?
Sir, someone has asked, after discussing regarding this one, you can discuss on current research going on Samsung with respect to secure software updates, particularly on firmwares.
Okay, I
In
can
the
tell
chat
you at
box
high
they have
level.
put.
Yeah, I remember Pradeep sir has asked. I can give you at high level because I can't disclose what is coming in the future. It would be company confidential, but I can talk about this a bit. No issue. Any other questions so far? Am I too fast? Am I too slow?
Participants, if you have any questions, you can ask. Sir, I hope no questions. You can continue, sir.
Okay, thank you very much. Now, coming to camera systems, this is one of the complex systems, and this is the number one buying factor. Or if somebody goes to the, to buy a phone, first decision depends on this camera. That's a survey result. So, camera is very critical for us. It has got multiple sensors, different focal length, many features. If you see, either you use any Samsung phone camera or anybody, that so many features are packed in. Why it is packed in? Because people like, some people like some features, some people like other features. We continuously strive to improve our camera. It is very important that any OEM vendor gives the better camera, because that's the decision factor. If we have a bad camera, that model will not sell in the market. So that's a constraint. Pack as much as feature as possible in the given system. These days, initially all the camera happened through computer vision, right? These days we are augmenting computer vision with AI and Gen AI. What it means is, right now more than 100 AI models are used in the phone, right? That's the level of AI which has gone in. These days, even generative AI is embedded into this phone. There are multiple LLMs. There are multiple LLMs or VLMs are there in the phone, so that the small device should run generative AI models also. Thing that's happening right now in this phone also. We support generative AI. It's both on device plus cloud. We have an hybrid thing, but so that's the level it should accommodate. So one at least 3 billion parameter model this phone should support, right? It's not easy to bring up in the memory your AI Gen AI models. So it's very challenging that point of view. The next is the lens alignment, stabilization, thin device. These are hardware challenges, so I'll skip that. But from software pipeline perspective, even the color, sometimes Indians like particular color, Chinese like different color. How do we set the color coding? All that is a very complex thing. So that's from a system point of view, bringing up the camera, bringing up all sensors, making it work together, the entire camera pipeline works seamlessly well. And whenever somebody takes a picture, how quickly you can capture it, how quickly you can do the background processing. There's a lot of background processing to happen. All those things, how do we do? So that's the biggest challenge. Next is about memory and storage. This is the critical piece, because any challenge in embedded system is the memory, right? It's always a trade-off. The algorithms we choose, depends on this, trade-off. Whether I have memory or I need performance, right? So that way we have to be very, very choosy when we do the algorithm. In some phones, we'll have a constraint on the memory. In some phones, we will have a constraint on number of background processes running. So we'll have to do a trade-off in algorithms. And this AI and Gen AI these days are consuming a lot of power and memory. For example, it will take 2 or 3 GB RAM itself once you load the thing. I mean, if you just load one Gen AI model. So those sort of things needs to be handled properly. Security and privacy. of course, nobody would like to have their data lost when you lose your phone, etc. So the entire phone, we have the trust-based security. We have two modes basically, one as a personal mode and another one for the office mode kind of thing. So all the non-personal things, that if it's this same device can act as work mode and personal mode. All the work mode is all encrypted and kept, so that even if you lose, it's all intact. People cannot. It's all encrypted. The keys are stored in the trust based chip there, etc. And also all the you get the frequent updates on all the things. So I would recommend you keep updating the security patches, because that's very critical. These days, the hackers are also advancing in a rapid speed. We have to make sure that everything works. Our encryption keys are stored in safe place so that it can't be broken. Hardware is a trusted thing. We have secure boot, OTA framework integrity as well. Also, I think Pradeep sir was asking about how do we do the downloading security aspects. We have something called as our Knox, Samsung Knox. It's a defense grade security solution is what we have. It's been approved by the US DoD as well. We supply these phones for the US security forces as well, because it's a defense grade security. So we have an entire Knox platform which will take care of the protection of all the content, and proper encryptions wherever needed. Even the binary download from our servers, everything is encrypted. We use the standard encryption keys, and we make sure that we are always updated on that. So the end-to-end security is very important for any OEM. A lot of testings do happen, and all those vulnerability will be fixed on real time. So that's my answer to Pradeep sir. Battery. Next is about the battery. Battery is very critical. These days people have less patience. They want fast charging. They want 10 minutes, 90% charging. A lot of Chinese brand do support this fast charging. But as per the current technology, the faster you use this charging, your battery life goes down. Meaning, you are using too much fast charging or too much high voltage charging, your life of that battery keeps reducing. So there is an optimal charging is what we need to do, so that the battery doesn't go bad. Otherwise, somebody who's using too much fast charging, and their battery, instead of 2 years or 3 years, that will go in 1 year. So that's one thing. We need to support the wireless charging as well as this non-contact charging. We need to heat dissipation is minimal. Battery health monitoring, we have a lot of algorithms in our office. Also, we check the battery health monitoring, etc. So this is one important piece in this software. Sensors, as I told you, accelerometer, gyrometer, biometric, hundreds of sensors. It should work together well. Sensors quality is important. If one sensor goes bad, some health related sensors goes bad, it can create issue in the market. We use a lot of sensor fusion for making sure that accuracy is not dropped, it's always improved, etc. So a lot of sensor related things is taken care during this software part. Now the other part, software is one piece, hardware comes from a different piece. How do we optimize everything? How do we make sure everything sits on one particular hardware? How do we software is written optimally for this particular hardware? Are there any unwanted piece of code, dead piece of code which is consuming processing power? All this, how do we use, what goes into CPU, what goes into GPU, what goes into NPU? NPU is also there. So this kind of architectural decision is very important. Any programmer would want to use NPU, and then hog it. It cannot happen. Trust me, maybe roughly for any, if I consider even the Android platform, more than 1 lakh people write software for it. More than 1 lakh people. All these 1 lakh people written software should come together, work together properly. If one guy doing some changes should not, if one guy corrupts the memory, it should not impact the others. Many things happens at the kernel level. Kernel level memory corruption is very easy, right? So many people working simultaneously, all their source code coming together, running efficiently, is one of the biggest challenge any OEM will have. Of course, right now, we have mastered that technique. We have mastered those systems, process, tools, etc. But somebody who is outside, just studying embedded systems, doing couple of things, this is in a very massive scale. It's unimaginable for somebody who's not seen this scale of the software being written. As I said, you can say 2.5 million lines of source code in any product is good. Then reducing bloatware. Many times what happens, somebody, we have software which we don't need, so we have to remove so that it doesn't consume any the processing power. As a phone manufacturer, we need to be very much concerned on the environmental and regulatory compliance. Uh, because these have this electromagnetic inference. So we need to be make sure that we are under the given guidelines. Our SAR limit, I would always recommend, if you're buying phones, if you're keeping in your pocket, please check the SAR limit for all the RF emissions. Typically, some of our competitors, they have high SAR limit, which is not good for our health. It has to be within the prescribed limit by the government. We try to use as much as sustainable materials and reduce the rare earth usage also. So as a company, we do that. So these are the main aspects in the design consideration, or it's a challenge as well. So that's a thing. So I'm open for questions. I'm not sure how much time I can go, but so any questions, please feel free. We can have discussions, and I'll be happy to address that.
Participants, do you have any questions?
I was expecting a lot of questions, but looks like not many questions.
Sir, can you tell me the hazards regarding the radiations of the mobiles?
See, there is something called as SAR value. I think you can check that on the phone package, or even in the setting you can check how much radiation it emits. It's called a specific absorption rate. So that if you check, it will tell you whether it is within the limit or not. So please buy phones with the SAR below the threshold set by the government.
And the thing is, regarding the resolution of the camera, sir, the pixels, can you tell regarding these things?
Yeah, because I showed you this, maybe.
Yes, you have shown, sir.
But I'll go back there. No worries. I'll go back there. My screen visible?
Yes, sir, it's visible.
Let me go to the camera aspect. You can see here.
Yes, sir, it's visible, sir.
Okay, so this is the camera specifications. People use camera either for image or video. That's the main thing. So we support in this device 200 megapixel camera. The focal length, the focal length is better. We support 24 wide camera. We have three sensors basically: wide, tele, and ultra wide.
Sir.
And yeah, 12, 10, and 200 megapixel is what we have. This 200 megapixel is the upscaling. Typically, it works in 12 megapixel. We upscale it to 200 megapixel with a lot of other things. For videos, it is 8K. So these are the camera. Important aspect of camera is this OIS also. OIS is important because otherwise, if your hands shake, the whatever picture taken will be blur. So we have this OIS support as well for the camera.
Sir.
So these are the important part. The zoom, another thing is zoom. There are two types of zoom. One is digital zoom, and the other one is optical zoom. Optical zoom is the hardware zoom. On top of it, we will have the digital zoom.
Digital
That's
zoom.
yeah. So this part of the story. And
Thank
videos
you.
also, videos also 8K you can record at 30 FPS. It's a good, resolution recording you can do with 8K, provided you have memory. 8K, 4K is very good camera. You have very to record good video.
Yes, sir. Sir, someone has asked the question, what is the SAR limit in India?
Let me check. I forgot because let me answer that. I don't remember right now, but SAR limit in mobile India 1.6 watt per kg or something. So I'll just check and let you know, because I don't 1.19 so some SAR limit is there. So 2 watts per kg, that's the thing, but there is some value. Please check that. I don't exactly remember the SAR value. Sorry. Watts per kg of the phone. So that's. Any other question?
Sir, in the chat box, Pradeep has asked the question, sir. Is Samsung working on developing OEM chipset which can replace Qualcomm Belite?
Yes, we have something called as Exynos. That Exynos, we have our own thing. So we use, for some products we use Exynos, which is ours. Otherwise we use Qualcomm. So we have multi chipset strategy. Yes, Exynos chipset will continue. We will continue to. We will not replace Qualcomm. Definitely no. Depending on the market, depending on the cost, we choose which chipset, which feature, etc. It will not be a replacement. Both will go hand in hand.
Participants, do you have any questions?
Coming to SAR, you can check your phone SAR by typing *#07#. That will tell you your SAR value.
SAR limit.
SAR limit.
Participants, do you have any other questions? Sir, hopefully no more questions.
Okay. Okay, I can drop off. Good enough.
Yes, sir. I'm going to thank you.
Okay. Thank you. Good to see you all, at least here. Thank you very much. Bye.
Okay, sir. Good evening, everyone. On behalf of SAHE and SSIT management, principal, HOD, and FDP organizers, I would like to express our sincere gratitude to Mr. Manu Prasad for his insightful and engaging presentation on mobile computing. Your comments about Samsung mobile hardware specifications were particularly impactful and resonated with many of us. We appreciate our sharing your expertise with us and hope to have you back again in the future. Thank you, sir. And I thank all the participants. Thank you a lot, sir.
Hello, madam. I
Hello, sir. Ha, sir.
Madam, I thank all the participants. I have one because I am also a resource person for the FDP. Can I, for the remaining anyhow, I have 30 minutes time. I'll just explain the CAN synchronization if possible. Shall I proceed, madam? For 10 minutes?
Yes, yes, sir, you can proceed. Yes.
Okay, okay. Okay, one second. Okay. So, I think you have yesterday, I think sir has explained you regarding CAN, okay, control area network. So CAN has two wires. Through two wires, I think yesterday sir has shown you how the ECUs are connected through the CAN. Okay, we have two wires. One is CAN H and CAN L. Okay, so through two wires, the entire ECUs are connected. So if I go for any of the microcontroller, if I take a standalone type of CAN controller, we have a trans receiver separate, we have a controller separate, and we have a microcontroller separate. Okay. If you take an integrated one, so we have the CAN module and the CAN controller together, but trans receiver is different. Okay. So here I'll just explain about the arbitration. So arbitration is a process in which, see, example, if many devices are want to communicate simultaneously, which device should be allowed. So that process, how our CAN will decide which device will be allowed to handle. So that is done through a process called arbitration. So arbitration, in order to do the arbitration, here they have given one example. So here you can see that. So before going for explaining all these things, CAN protocol we call by the this CAN protocol is an message control protocol. Means for example, we have a WhatsApp group. In that WhatsApp group, we are putting some message. So the person who required that message will take that message, remaining will discard. In the same way, so all the devices, many devices, many devices are connected to the CAN using a through same two wires, but the devices which required that message will take it. So for that reason, we call it as a message based protocol. So consider 3-4 devices are there. They want to send the information simultaneously. So the one with the lower message ID will won the rest. For example, you can see here. So we have the three message IDs available. So 7F3, 6B3, and 6D3. So all are sending the information. The one with first 0. So here you can see that node 1, node 2, node 3, all the 4 are sending the information. So here all are sending 1. So no one has won the race. So in second bit duration, we can see that 3 of them are sending all of them are sending 1. So in third one, 3 of them are sending 0. So 0 will be considered as dominant bit in CAN, and 1 will be considered as recessive. So these three devices have won the race, and this node 1 has lost the race. Okay. So next, once again, we have all the one here. So among these three devices have one here. So for that reason, no one has won the race. So when we go for third next duration, we can see that your two devices, that is node 2 and node 3. In this node 2 is 0 and node 3 is 1. So for that reason node 2 has won the race. So this one we call by the name as our arbitration. In here through this arbitration mechanism, node 2 has won the race. Means the person who put first 0 will win the race. Okay, so that is our arbitration. So out of the three devices, the device, the one with who puts first 0 will win the race. Okay, once the race is won by that node, so the whatever the information that lines are free for the node 2, remaining node 1 and node 3 will keep quiet. So they will not send the information. Okay, so here this is the one. So if they are wishing for sending, so how the other devices know that they have lost the race. Okay, so in order to know that one, what we are doing is, see, for example, node 3 is sending 1, but CAN bus, at the output of the CAN bus we are getting 0. So each device is connected to the CAN bus. It is sending as well as receiving the same information in their controller. So it is, if it is sending 1 and if it is receiving 0. Okay, okay. Okay. If one is sending 1, for example, node 3 is sending 1, but it is receiving 0, means at the transmitting end it is 1, but at the receiving end it is 0. It indicates that whatever it is sending, it is not receiving. Okay, so means it is not our it indicates someone else is sending 0. For that reason, it is, we are getting 0 at the CAN bus. So then what it will do, it will come out of the race, or it will not send the information. So the once the race is won, so the device will send the information. Okay, so that is about the arbitration. If the node detects the dominant bit on the bus while it has transmitted the receive bit, it means that the node has lost the arbitration of and stopped transmitting the further bits. Okay. So now if I go for the frame, how the data will, hello?
Sir, can you please explain that arbitration when it wins, what is the voltage of that for 1 and zeros, usually in CAN?
Okay, 1 second, I'll check it. Okay, here you can see. So for CAN H, the voltage, if I want to send 0, okay, if I want to send 0, CAN H, we have in the CAN H wire we have to send 3.5, and in CAN L we have to send 1.5. So if I want to send 1, so at that time both CAN H and CAN L will have an voltage equal to 2.5. Okay, once again I repeat. So in CAN high and CAN low, if I want to send 0, if I want to send 0, CAN high should have an voltage equal to 3.5 and CAN L should have an voltage equal to 1.5. If I want to send 1, so then so both CAN H wire and CAN L wire both will have an value equal to 2.5. So you can observe here, for sending 0 we have a different voltage. So 3.5 and 1.5. So if I take a difference, I will get an value equal to 2. And for sending 1, so the value is 2.5 and 2.5. If I subtract it, we are getting an value equal to 0. So for that reason, the 1 is recessive here and 0 is dominant. Okay, so this is the way how the data is sending. So now
Whether it is compulsory that we have to use the 3.5, why we are using particularly 3.5, 1.5?
yeah, it is an standard actually. It is an standard. So CAN standard, how it is set by the Bosch, or we can change it, but there should be a difference. Okay, so because you know that in car we have many devices connected, so we have to go for a longer distances, right? Means within the car the data should travel for a longer distance. So if the voltage is very less, so then it is difficult. Okay, so the difference should be at least 2 volt or more than that one. Okay, so we can set it depending upon the requirement, but as I know, so this Bosch is using this standard.
About that service IDs, so three service IDs which will gain the arbitration. Whether those values are fixed or something like that, we are using some standard values for that to win the arbitration, some 7E, 6E.
Okay. So here what happens, consider we have a temperature sensor. So temperature sensor is important, or consider we have an what we call door sensor or something, okay, which is very important. Okay, so that should be given a lower message ID. For example, let us take temperature sensor only. Temperature sensor is having a message ID as 01. So if in a boiler or somewhere, if the temperature goes more than some limit, it should we have to reduce the temperature. If you don't reduce it, the boiler will break out. So for that reason, what we are doing is we'll set an message ID for the temperature sensor as 01. So the CAN connected or the ECU connected to the temperature sensor will send the information with a message ID equal to 01. Okay, others are also sending the information. So but this is having the higher priority. So for that reason, so all other devices are receiving that information. So information coming from message ID 01 will be given first preference, and it will take the action. Okay, so that devices like a cooler or something will take the action, and it will reduce the temperature of the boiler. Okay, so it is a message ID. So if we go for I2C and other protocols, there what we are sending is the destination ID. So where I want to send the information, that destination ID we are sending. We are not sending the message ID. So if a person is sending, if I want to send a data from 1 to 2, so I am sending 2 with my data. So the person with lower message ID, with lower destination ID will win the race in I2C bus. But here it is not like that. The message ID is the important information of the device. Okay, so which should be received by everyone, and the one who required it will take that information. So message here, whatever the value I am giving here, the ID what we are using in CAN is the message ID. Okay.
Sir, a particular number is there, that 7E, 6E. So whether they are data frame values or else just it is designed that 7F3 is the value. So why only 7F3, 6B3, 6D9?
No, this is just an example. This is just an example. Consider a device is there with a message ID equal to 7F3, 6B3, 6D3 like that. Okay, if a device, if these three devices are there, these three devices are sending the information with these message IDs. Okay, so then the one with lower message ID. So here you can see that the one with the lower message ID is 6B3. So this will win the race. So but how here through program we can identify, but in your wire we have ones and zero. How to identify that which has won the race? So we are taking here this thing. So first we will check the one who put first zero will win the race. Okay.
Okay, sir. Thank you.
Okay. So I'll just explain about the format of the CAN. So what are the things present in our CAN? So if I want to send the data from one device to another device, what procedure we have to follow? So here we can see that first there is an ideal bus ideal thing. So send off here we have start of frame. So start of frame will be generally 0. Start with 0. Then we have an identifier. So if we go for standard CAN, we have 11 bit. If we go for extended CAN, we have 29 bits. Okay, 29 bit identifier address. So if we have 11 bit, 2 to the power of 11, so approximately 2048. So many bits to so many devices I can connect if I use the standard CAN. If I use the extended CAN, we can go for 2 to the power of 29. So many number of devices we can connect through our extended CAN. Okay. So first the information what we are sending is the bus ideal thing. Then we are sending a startup frame. Then we are sending the identifier. We have an RTR bit. So RTR bit will decide. So this bit, the after 11 bits, this bit will decide either I am using the standard CAN or I am using the extended CAN. If this bit is 0, then it indicate we are using the standard CAN. And if I give this bit as 1, so then it indicate the, if it is 0, then it is standard. If it is 1, it indicate the extended CAN. So if it is extended CAN, so there is an format for extended CAN here. So along with our 11-bit address, we'll send the remaining address. Okay. So next is your IDE. So this IDE will decide identifier extension. If it is 0, then it is a standard 11-bit. And if it is 1, it is 29-bit ID. Okay. Remote transmit. So then we have an DLC available. So DLC is data length code. So how many bits we are sending? So either we are sending 1 byte of data, 2 byte of data, 3 byte of data. So that information is present in our DLC. So if I give 001, then 1 byte, 010 means 2 byte, 011 means 3 byte, like this up to 8 bytes. So we can send through our CAN maximum 8 bytes of data we can send it. So next is your CRC. So 15 bits of CRC code will be there. So cyclic redundancy code will be there. So for the data means from here to here, from your identifier up to the data field, for all the bits it is calculating the CRC, okay, cyclic redundancy code, and this cyclic 15 bits of cyclic redundancy code will be taken along with one delimiter. So that is 1. Okay. So generally delimiter will be 1. It's a difference between, it will separate our CRC with the acknowledgement. Okay. So next is the acknowledgement field, and once again, so lastly we are sending EOF, that is end of frame. Okay. So so here as I told, this is our standard one. So CAN standard data frame. We have an bus IDL SOF. So we have an identifier RTR. Okay. So means 11-bit address will be present here. Okay. So here if I go for extended CAN, so here we have some more bits available, that is base identifier, SRR, IDE, extended identifier. So RTR, R1 and R0 and plus DLC. So these are the extra things which we are sending if we are using the 29-bit data. Okay. So this I told you, sorry. So here we have RTR bit, that is remote transmission request. Okay. So this bit will decide either I am asking the information or I am sending the information. Sorry, I have forgotten to tell this. RTR it indicate. So for example, I am a boiler. I want the information about the temperature. Okay, means I am a cooler and I want an information about the temperature of the boiler. So I am requesting, my ECU is requesting to the temperature sensor regarding the temperature. How to request it? So for requesting also I am sending the same identifier. So for example, I am putting the identifier of the transmit temperature sensor, and I am sending a value equal to 1. So if I put 1, it indicate that I am requesting the information from that temperature sensor. So once that value is received by the temperature sensor, it will identify that yes, I am someone is asking for the information about the temperature sensor, and it the temperature sensor a attached ECU connected to the temperature sensor will send that information on the bus. Okay. So that is about the remote frame. The purpose of the remote frame is to seek the permission for transmission of data from another node. It is similar to data from without the data field or data RTR bit is, otherwise the RTR bit is recessive. Okay. So DLC, as I told, just whatever I have told, this control field will be there. Okay. So 0 means data frame. So we are sending the data, we are writing something. 1 means we are reading remote frame. Okay. we want some information from someone. So at that time, I'll send it with a value equal to 1. So end of. So like this, the data will be sent. See here, you can have many nodes connected to the same uh, wires. Okay, same wires are there. To this same wires, we can connect the many devices. Okay. So I think you know about the CRC, okay, cyclic redundancy code. So this is used for sending the while sending the data. If number of bits, how many bits we are sending. For example, for security purpose, for securing the data, we are using the CRC. Okay. So because we are sending 15 bits of CRC code, CRC value. So the polynomial what we are using is 16 here. Okay. So 0 to x to the power of 15. So 16-bit polynomial we are using for this one. Okay. So I think you know how the CRC will be calculated. For example, here they have given one small example. So this, if this is my data and this is my polynomial. Okay. So if I want to, so here the value is 1. So first bit is 1 and this is 1. So we'll put it 1 here. Okay. So I think you know about this. So like this, we are going to calculate about the CRC, and then that CRC will be used for sending the information. Okay. So we have different types of error, that is bit error will be there. So if bit error detected by transmitting the dominant and monitor the recessive on the bus and vice versa. So if someone is sending 1, if some device is sending 1 and if we are receiving 0, so then that there will be a chances of error. It indicates some error. So that type of error we call by the name as bit error. Stuff error means it is detected when the bit stuffing is violated. If 6 consecutive ones are coming, consecutive bits of same polarity is received, then it indicates so there is a stuff error. So what happens now while sending the data, we will not send the data directly. We will use bit stuffing. In bit stuffing, if we have a continuous ones, so if we are having continuous 5 ones, we will put 1 0. If we have continuous 5 zeros, we are putting 1. So from this, what happens if we get a continuous 6 dominant bits, or if some recessive bits are obtained, so it indicate some data problem has occurred. Okay, so that one we call is a stuff error. So form error, if there is a proper format is not violated, if the format what we are using is violated, so then it will create an form error. Okay, and you know about the CRC error. So here whatever the data I am taking, so at the end, so this is my transmitting. While transmitting, I am sending the data like I am calculating some value here. So this is 001 is the remainder what I obtained along with my data. So this is my data actually 100100 is my data. So how many bit of CRC I want to send? 3 bit of CRC I want to send. So 4-bit polynomial I have taken, and I have taken the remainder. In simple words, I have taken the remainder. So this remainder I am placing here. I am adding that remainder with my data. So for example, if I take 5 divided by 2, I will get a remainder equal to 1. So 1 if I add to 5, so I will get 6. Okay, at the receiver end, I will divide 6 by 2, I will get a 0. If I get 0, it indicates so the data what I have sent is correct. If I don't get 0, it indicates the data is wrong. In the same manner, here you can see that at the receiving end, I am once again I am using the same polynomial and I am dividing it. So if I get 0 as a remainder, it indicates so the CRC what I have sent or the data what I have sent is correct. So this if we don't get the information properly, so then that error we call by the name as CRC error. And we have an acknowledgement error also. So if we are sending some information, if to someone after, if you don't get any acknowledgement slot, okay, so then that error we call by the name as acknowledgement error. Okay, so here you can see 6 dominant error frames. We have 6 dominant bits and error frame delimiter. So 6 6 Okay, if we get 6 zeros, then also an error frame. Okay, so once again we have an different types of error frames. Active error frames will be there, and passive error frames will be there. Okay. Okay, I think this is not required. Okay, I think I have explained about the arbitration. So if anyone have the doubt, if the participant have the any doubt in arbitration, they can ask.
Okay, Dr. Ghouse, sir.
Yes, sir.
I'm Sunil
Yes, sir.
here.
Yes.
Actually, arbitration is a binding procedure, right?
Yes, sir.
So who is going to administrate it?
Sir, it is means no one will administrate it, sir. So all the ECUs are connected through the this CAN bus. So electronic control units are there. So that electronic control units are nothing but the microcontrollers. Okay. So that
So
microcontroller.
microcontroller is going to have the control over the arbitration, right?
Yes, sir. Yes, sir. Actually,
How?
the microcontroller, the transmitter, they only will understand. So while I'm sending the data, is the data what I'm sending is properly going through the transmitter or not? So you can see here. One second, I'll show you the.
Now, for this arbitration,
Yes, sir.
is there any service providers are there so that they are controlling the devices to prioritize?
No, sir. No. So the ECUs itself will decide by themselves. Okay. No
How
one
it is
will
going?
control it. No one will control because we have a trans receiver present, and here you can see here, sir. So only devices are there, no any other things are connected. Okay. So in the ideal condition, this both are at 2.5. If both voltage are at 2.5 for a longer duration, it indicates no one is sending any information. So if someone want to send the information, first it will check for the voltage levels present here. Okay. So here we have an resistance 120 ohm resistance will be there connected to an pull up resistors. So it will check both are at an high level of 2.5 volt. So it indicates that the data no one is sending the data. If no one is sending the data, then the device will put the data on the bus. Okay. So if more than one person is sending the data, during that time one will come, means other ECUs will understand that some higher person is sending the data, means a person with a lower message ID is sending the data, and remaining will come out from come out of the transmission process. So how the ECU will know that the data is the CAN bus is busy, means through the error bit. If it is sending 0 and if it is getting 1, or if it is sending 1 and it is getting 0, it indicate someone with higher priority is sending the data, and now they will wait for end of frame. Until the end of frame is obtained, no one will send the data. At the end of the CAN, we are sending the end of frames. So this end of frame, continuous 11 bits, I think I forgot. So continuous 11 bits of ones will be there. So that way, that indicate the end of frame. So because you can observe here, because of bit stuffing, so we are no bits means continuously if we are getting 0, if after 5 zeros we are making 1, after 5 ones we are making 0. So because of that, during data transmission, there is no chance of getting continuous 11 ones. Okay, if we are getting continuous 11 ones, it indicates the end of frame, and once the end of frame is obtained, the device will understand that the transmission process is over. So 7 bits, sorry, 7 bits, continuous 7 bits will be there. If they get continuous 7 ones, it indicates that the data is it indicates that no one, the person who has sent the data, say was sending the data, has completed his operation. So they can send the data, means they can go for their turn. It's okay,
So
sir.
how it is going to enforce or enforce the force the devices that is, so the arbitration
Yeah, sir.
is usually awarded for the final and enforceable, right?
Yes, sir.
So how it is going to force the decision?
1 second, sir. I'll show you.
Can.
I'll show you, sir. So this is the method what we are using. So CSMA carrier. So that is collision detection mechanism. We are carrier sense multiple S's and collision decision mechanism is used by the microcontroller, sir. So here you can see. So the microcontroller CAN bus is not alone. This is just an bus, sir. So this CAN H and CAN L is just an wires. So they will not decide actually. So in the CAN we have a separate CAN trans receiver present. So that trans receiver, what it will do, it will convert your CAN voltages. So it will decide either the whatever the data. Here you can see that the name is trans receiver. It is transmitting as well as receiving. So simultaneously it is doing both the things. Okay. So while it is sending and receiving, if it get some error, so then it will decide. So who will decide? This controller will decide. So the data what I am sending and the data what I am receiving is not correct. So at that time, so the CAN controller or the CAN protocol controller is there. So that will decide the how the process this arbitration and other things along with the microcontroller. So in some of the devices, in standalone CAN controller, we have this trans receiver separate, we have the controller separate and microcontroller separate. If you go for an integrated one, like if you go for LPC 21, if you go for 2148 or any other devices, we can see that this microcontroller have both the inbuilt along with our ARM controller, we have this CAN module, but we have to connect the CAN trans receiver separately. Okay. So
Okay, sir.
this
Thank you.
is the process. Like this, they have designed the device, sir. In some devices are there. Some now, if you go for ESP32, advanced ESP32 devices and other things, so they have all these things in a single bus, sir. Means the one which are using this CAN H and CAN protocol devices. Okay. So here you can see that all nodes must sense the bus before transmission. So that is carrier sensing and equal access opportunity for all the nodes. It must detect the collision during the transmission. Once the collision is detected, the distributed arbitration will be applied. So this is the mechanism. It is used in general our LAN and other process also, but here it is done through this mechanism, sir. Any other doubt? So is it over, sir? Is it okay, sir? Sunil, sir?
Okay, sir. Okay. Thank you.
Okay, sir. So any other? Okay. Okay.
Okay, sir. No participants, any doubts? Hopefully, sir, no other doubts. Okay,
Okay.
my sincere thanks to Dr. Ghouse Ahmed, sir, who has explained neatly regarding the CAN control architecture and its arbitrations. Thank you, sir.
Thank you, madam. I request the participants and to make your videos on so that we can take the um, photos, snapshots. Okay. So I think 1 second. Either stop madam.
Sir, you have disabled my video.
No, you should enable, madam.
No, host has disabled my video.
Hello. Hello.
Hello, madam. I
Ah,
thank
so,
Ashwini
sir.
madam for I thank Ashwini madam for engaging very well. Okay, this session. Thank you,
Tha-
madam.
Thank you, sir. Very much.
Once again, thank you all the participants for your patience listening. And it's an humble request that we are going to send a Google feedback form on each session. Please do fill it without fail. Thank you. Thank you. Good night to all. Thank you.
Thank you, ma'am. Good night.
Good night, madam.